Split screen. I don't know. That's just uranium. Oh no. All right, so I guess we could start on atomic radius, ion radius, so size. So generally for, let's figure it out together. All right, so atomic radius, we want to know how things get bigger. So we check the periodic table. We think about like hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. All of these are in group one. So if we do just the outer electron configuration for them, just to see them, we have 1s1, 2s1, 3s1, 4s1, 5s1, 6s1, and then 7s1, like that. So if you notice, they each have one electron in the S subshell, but they're just on different energy levels. So as you go down a group, what's happening, the atomic radius is getting bigger because that electron is getting farther and farther away from the nucleus. So let's pretend hydrogen kind of look like this with the nucleus in the middle. 1s might look like that with your one electron in there. Lithium, not only does it have that 1s, but now it has the 2s. Sodium, so it has the 1s, it has the 2s electrons, and it also has 3s electrons. Potassium has the 1s, 2s, 3s, and it has the 4s. So as you can see, as you go down a group, you're increasing the number of energy levels. And as you increase the number of, as you increase the energy level, you're just getting bigger because you're literally just adding layers and layers and layers to the atom. So that's why going down a group, you're increasing the atomic radius. Those subshell shapes. So that's the group trend for atomic radius. So if we talk about the periodic trend, atomic radius, or the period trend, because it's getting bigger. So notice how the circle's getting bigger and bigger. That's why it's getting bigger. Whereas francium, it'd be the nucleus with 1s, 2s, 3s, 4s, 5s, 6s, 7s. It's getting bigger and bigger. So for the period trend, let's look at sodium versus argon. Both of them are in the third energy level. So actually, let's look at, so it's easier to see the similarities. Let's look at aluminum versus argon. They both have electrons in the 3s2, 3p. This one's 1, 2, 3. This is 3s2, 3p6. So they both have their highest energy level as energy level 3. But aluminum has 13 protons and argon has 18 protons. Meaning, if we just simplify the atom and have all 13 electrons, or let's look at the valence electrons, all 5 valence electrons with a nucleus of 13, let's change it to 13 protons, versus argon has 18 protons with 8 valence electrons. What's happening is they're both in that third energy level, and you're looking at, okay, these 18 protons, they're trying to pull those electrons a little bit closer to them because protons and electrons attract each other. So that third energy level is actually going to be a little bit smaller because those 18 protons are going to be doing a better job at pulling in those electrons. Whereas compared to the 13 protons, they're going to pull on the third energy level a little bit less. So that's why as you go this way, it's getting bigger due to the weaker attraction from the nucleus. The pull from the proton is weaker when there are less protons. Correct. Because if you can imagine, the nucleus is pretty much trying to bring down that energy level. So for aluminum, you have 13 protons that are pulling that third energy level down versus 18 protons pulling that energy level down. 18 protons are going to do a better job of pulling it down. So the overall trend for atomic radius is that it increases to the left due to the weaker nuclear attraction and going down because you're getting increasing energy shells. So it increases for that. So if you remember the atomic radius, the other two trends are just exact opposite atomic radius. So it's a little bit easier that way. So let's see, 0 to 10 minutes. We talked about atomic radius. Let's go with ionic. So ion size. Let's look at aluminum. We have aluminum and then aluminum. Aluminum has how many valence electrons? It has 3. Meaning between going to 8 to get a full octet or getting rid of its 3 electrons, it's going to most likely get rid of the 3 electrons. And if you lose 3 negative electrons, you become a positive 3 charge. No, aluminum is just a metal. So now if we look at that, if we look at the electron configuration for aluminum and the aluminum ion, we have 1s2, 2s2, 2p6, 3s2, 3p1. Whereas aluminum is 1s2, 2s2, 2p6, because we got rid of 3 electrons. So now if you think about it, the aluminum ion or aluminum atom will have that, let's pretend the 1s 2s, and 3p, or 3s, all the way to 3p. And then the aluminum ion, however, is just going to go 1s, 2, meaning the aluminum is going to be bigger because the aluminum, it goes all the way to that third energy level, whereas aluminum ion only goes up to the second energy level. Remember, not everything that touches the staircase is a metalloid. So if you think about aluminum, you use aluminum to really wrap like your leftovers. Aluminum is a metal. Yeah. So ion size. So if you always think about it, if you're removing electrons, you become a positive ion. So you become a cation. And if you become a cation, if you think about it, as you remove layers off of an onion, what's going to happen to your onion? Your onion's going to get smaller. So same idea. So as you remove electrons, you're getting the onion to get smaller and smaller. The atom will become smaller and smaller. Yeah. So ion size part 2 is when we look at the anion. So things like, let's go with nitrogen. Nitrogen has 5 valence electrons, so between going to 8 or 0, it's easier to gain 3 electrons to fulfill its octet. So nitrogen will have a tendency to become -3 ion. So if we do electron configuration, 1s2, 2s2, 2p3, 1s2, 2s2, 2p6. So now you look at it, you're like, all right, yeah, it would do either. So nitrogen right here has the 1s, or the first energy level, second energy level. And you would assume, okay, nitrogen ion has the same thing, first and second energy level. But now if you look, the nitrogen atom has 5 valence electrons on the very outside, whereas nitrogen ion has 8 valence electrons. Same number of protons, they both have 7 protons in the middle. So those 7 protons are now trying to control 8 electrons rather than 5. So not only are there more electrons to kind of share that the protons in the middle, but there's also something called electron shielding. That's more so as you go down the levels. But basically, as electrons kind of move in front of each other, the attraction from the protons are less for the ones on the outside. So they're going to be a little bit farther away. So then if you just think about it, if you add electrons, you're kind of like adding layers to your atom. So that's why it's going to get bigger. So same idea. If you add layers to your onion will get larger. So general rule of thumb, the anion will be bigger than the neutral atom, and the neutral atom will be bigger than the cation. So pretty simple, because as you're adding the electrons are, you're just literally adding layers to your atom. Good, so that's ion size. Next, let's talk about ionization energy. What is ionization energy? Nope. Nope. Oh, yeah. What Crucial said. I didn't even see you type that. The energy used to remove an electron. That's just ionization energy. So when you're thinking about this, I thought you said that necessarily. No, you said add or subtract electrons. Not really. So Crucial is right. Energy used to remove one electron. So if you think about it, if higher the ionization energy, if you increase the ionization energy, this requires more effort to remove that electron. So more energy means it's harder to remove that electron. So now let's talk about the trend. Group trend. So we go back to comparing lithium to francium. 7s. So now we compare lithium, which is 1s, first energy level, second energy level, and francium is first energy level, second energy level, third energy level, fourth energy level, fifth energy level, sixth energy level, and seventh energy levels. Hopefully you could already tell that francium is larger than lithium. So now imagine all the protons in francium, all the protons on lithium, need to control all the electrons on the outside. So for lithium, there's 2 electrons in the 1s. So I'll use a different color. So here's 1, 2, and there's 1 electron in the 2 energy level. So for francium, it's a lot more difficult. There's 2 in the 1. There's 1, 2, 3, 4, 5, 6, 7, 8. In the second, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. In the third, 1, 2, 3, 4, 5, 6, 7, 32. Let's pretend I did 32. Then there's 32 more in the next energy level, 32 more in the next energy level, 32, right? 18 plus 14, yeah. 32 more in the next energy level, and then 32 more in the next energy level. Yeah, so now imagine, all right, in order to lose an electron, which element is more likely going to lose one electron? Francium. Francium is more likely to lose an electron because it has to control all these electrons, and all the only way to keep the electrons in check is from the protons right there. So imagine, let's pretend this electron right here. This proton has to make sure that it's attracting this electron right here. The chances, how much energy you actually have to put in to like remove that electron, probably not that difficult. You just take it and then you remove it. Whereas this one, if you try to remove this electron, these 3 protons are just holding on to this electron, and this electron. So it's going to be a lot. You have to put in more energy to try to grab this electron and try to remove it, versus this one where you just grab it and then you can just pretty easily remove it there. So as you go down the group, the ionization energy decreases, meaning it's easier to remove an electron as you go down a group. But to keep with the same thing, we like to do, as you go up a group, ionization energy increases. So now let's talk about, so my analogy here is, I already told my class, but you're walking your dog, your name is lithium, and you're walking your dog, your name is francium. Lithium is walking their dog right here. Does any of you know boys water polo won today? Versus Francium, remember, Francium is all the way over here. Wow. So now, I don't trust you, Ryan. There's a person here trying to steal your dog. They have scissors. They're mad, and they have a bag. Ready to steal your dog. Did they actually lose? No way. I can't trust you either, Keller. No way that they lost. They said they were going to score 10 in the first quarter. I don't know even how to check. So at this point, if you're trying to remove this dog, so this dog represents the electron, which one would this thief have an easier time removing that electron? Francium, because all it has to do is come all the way over here, cut the leash right here, and then take the dog, and it's home free. So it'll take more energy for you to take this dog because this dog is closer to the nucleus. So that's essentially what's happening here when we were drawing the actual atoms. So now we have to talk about the period trend. So the period trend for ionization energy. Let's look at aluminum versus argon again. And so let's look at aluminum and chlorine. They're both in the third energy level, so their highest energy level is third energy level. So aluminum has 13 protons, and let's just draw like that. So this is the third energy level. Chlorine, same thing, third energy level, like that. But chlorine has 17 protons. So aluminum, there's some electrons on the outside. These 13 protons are trying to attract those electrons in. Versus now these 17 protons are trying to attract these proteins in. Which one has a stronger pull on those electrons? Yeah, chlorine. Because chlorine, there's 17 protons holding on to all those electrons, whereas for aluminum, only 13. And they're at the same level. So it's going to increase going this way. So the general trend for ionization energy is that it increases going up and across. It's the opposite of atomic radius. So we go back to our dog example. I guess we'll go with lithium and we'll talk about fluorine. So here's fluorine. So fluorine, remember, fluorine and lithium, they're both in energy level 2. So the relative distance to their electrons are pretty similar. However, fluorine has how many protons that are trying to hold on to its electrons? It has a lot more. So now what you're essentially doing is having a lot more leashes on your dog. I guess I could try to move the dog so it's on the right side of lithium. So now, lithium only has one leash on its dog, whereas fluorine has all these leashes on the dog, keeping its dog safe because it has more protons holding on to the electrons. So if this thief were trying to steal this person's dog right here, the thief would need to use a lot more energy to cut through all of those leashes to finally steal the dog. So that's why for ionization energy, it increases going up and to the right. Increase. That's ionization energy. Yeah, we're just the leashes are more so showing you the attraction between the protons and the electrons, but similar. So 15 to 27 minutes we talked about ionization energy. We'll take a quick break right now to see if water polo won. Meters, school, boys, water polo. Let's see if they won. We did win, but they were held scoreless in the first quarter, 13 to 2. Good job, boys, water polo. First Edison, 13 to 2. Where is it posted? Just online. I just Googled it. All right, so next, electronegativity. What is electronegativity? Yeah, so it's the ability for an atom to gain, not gain an electron, but gain an electron. So ability to gain electron. So let's talk about the group trend again. So group trend first. We're picking on lithium and francium. So lithium is a 2s1, francium is 7s1. So now imagine there is an electron right here. What part of an atom is attracting the electron? Yeah, so since electrons are negative, the positive protons are attracting the electron. So if you think about lithium, lithium is energy level 1, then energy level 2. Whereas francium, energy level 1, 2, 3, 4, 5, 6, 7. And lithium has 1, 2, and then 3 electrons, whereas francium, I'm just going to arbitrarily draw a bunch of electrons right around. So francium actually has 87 electrons. Yeah. So really the only difference between lithium and francium is that one is only 2 energy levels big, other one is 7 energy levels big. So now let's look at lithium. It says lithium tries to gain this electron. Lithium could get pretty close because the part that's trying to attract the electron is the proton. So let's move it as close as possible. Let's see right there. Whereas francium, let's try to get close. So something about right there. So now if we look at their nuclei to see how far it would need to try to attract. Lithium's nucleus is about that close to the electron, whereas francium's nucleus is that close. And another thing is, what's in the way of francium's nucleus to try to attract one more electron? What's like getting in the way of the protons in the center of francium with that electron that's trying to attract? Yeah, the other electrons. The other electrons are all in the way, so they're kind of shielding and blocking off the proton's attempt to try to attract that electron. So if you compare lithium and francium, electronegativity is going to increase going up. So that means it's better at um, gaining an electron. Yeah, has much less to get to that electron. So that's the group trend. As you go up a group, you're getting rid of layers off your atom, meaning your interaction from your nucleus to the outside, that distance is a lot smaller, so its interaction could be a lot stronger. All right, so then the story with this one is you have a dog. It's like standing on its hind legs. That. And then you have one person right here, and it has a fancy chicken flavored proton. And you have another person over here, also with a proton. Which one is this dog gonna be more attracted to? This person or that person? Yeah, the person on the right, because that proton is a lot closer to this electron versus this proton is trying to attract this electron, but there might be like a bush in the way, a tree in the way. So that proton's going to have a harder time trying to attract this electron to get to it. So that's that. Next is period trend for electronegativity. Period trend is, let's make fun of aluminum and chlorine again. So they're both in the third energy level, so distance doesn't really matter. So aluminum has 13 protons, and chlorine, similar, will have 17 protons. So size doesn't matter in this case as much. Granted, chlorine is still smaller, but let's pretend. So here's an electron. So it could get about this close, and then this one could get about this close. So distance-wise, the nucleus to the electron, is there any real difference? Not the answer to my question. Is there any real difference between the nucleus and the electron? Yeah, more so just the pull, not the distance, because granted chlorine is going to be a little bit smaller, but if you look at the third energy level to the third energy level, it's pretty similar. So now you're just looking at the number of protons. The number of protons are pulling on that electron. You have 13 protons trying to pull this electron, but then you have 17 protons pulling on this electron. Which one will do a better job at taking that electron? Chlorine, because there's 17. So if you ever played tug of war, if everyone is equally strength, the side with more players will win. So then the story about this one is there is a dog and there are some treats. Put that up there. It's a dog. See pointy ears. It looks more like a cat now. And remember, the people are generally around the same size, same place away. But what was the only difference between chlorine and aluminum? They're both on the third energy level. Yeah, the number of protons. So now instead of having just one yummy chicken flavored proton, this person has a bunch of yummy flavored protons, meaning this dog is probably going to want to go this way because there are more protons attracting that electron. So the overall trend for electronegativity is that it increases going up and to the right across, excluding which group? Yeah, the noble gases, so group 18, because noble gases, they don't want any more electrons, so they have no real need to try to steal an electron away. So good. So those are all the trends. You guys want questions that I could give you? Wrong accent, man. All right, so questions I could give you. Alexander, if you look at the topics to cover, we have electron configuration under topics. If let's go back to the homework so that I don't have to type it. Ambient selection. There's one. Ready, set, go. Which half? Right or left half? Right. Does that help at all? Ready? You want me to talk about it? Ready. If you're ready, type in your answer. Oh, dude, talk about it. Still. No comprende. Your Spanish is wrong. There you go. All right, let's talk about it. So the first one, elements A and B are in the same group. Element A has an electronegativity value of 3.5 and B is 3.8. So remember, we know you should remember that for electronegativity, it increases going up and to the right. Same group tells you that we don't care about the going to the right part because same group is vertical. And we're increasing going up. The 3.8 is the larger number than 3.5, so I can verify, yes, I did increase. 3.8 is my BA. So then on the test, you'll say something like B is above A or A is below B. So both of those say the same thing. For the next one, elements A and B are in the same period, and we're talking about ionization energy. So ionization energy, same thing, increases going up and to the right. Same period tells you, hey, we don't actually care about the going up part, so we only care about going left and right. A has an ionization energy of 199 kilojoules per mole. Element B has 335 kilojoules per mole. So I'm increasing going to the right, so I'm going to put my 335 here, my 199 here, and that's going to be B to A. So if I look, yes, it's increasing this way, so then I could say like A is to the left of B, or I could say B is to the right of A. Same, same. Then, for which is the largest out of the 1, 2, 3, 4, 5, 6, 7, 8 atoms I gave you, couple things that you could do. You could first look at the ions. So between all the ions, what's going to be bigger, fluorine or fluorine ion? The ion. So you could get rid of that. So you know if it's going to be fluorine, it definitely won't be the fluorine atom. Between bromine and bromine ion, which one is going to be bigger? Ion. Sorry. All right. So we could get rid of bromine. Between strontium and strontium ion, which one's going to be bigger? The atom, right? The neutral atom. So we get rid of this. Same thing with getting rid of cesium. So now our real answer choices are fluorine ion, bromine ion, strontium atom, and cesium. That's when you go to your periodic table and then you say, all right, fluorine is here. Actually, do I have a periodic table that I could share with y'all? Share, recently shared. Um, There it is. So I forgot all the ions we were focusing on. But I remember one was fluorine, one was bromine, one was strontium, and one was cesium, like that. So now if we look at this, atomic size we know increases to going to the left and down. So increases for atomic size. So then if you want, you could also do it this way where now you're comparing each element. So you could have like basically like a little tournament. So we already figured out between fluorine ion is going to be bigger. But now if you compare fluorine with bromine, which one's going to be bigger? Bromine. So that means you could actually get rid of all of the fluorine options because we know bromine will be bigger. But now if you compare bromine with strontium, which one's going to be bigger? Strontium. So you could get rid of bromine. All right. So now between strontium and cesium, which one's going to be bigger? Cesium, because remember, we're continuing going to the left and down. So strontium. So now your only option is really between cesium and cesium ion. And in order to become a positive ion, cesium lost an electron. So that means you are losing a layer off your atom. So which one is going to be bigger, cesium or cesium ion? Cesium. So that's how I would go about answering those questions. So if you're given a list of elements, just look at all the elements where they are on the periodic table and just slowly start to eliminate them as you go like from one to the next and next. So it's important that you remember these trends. They will help out a lot. All right, so this is 38 to 51 minutes. We talked about periodic trends practice. All right, so electron configuration now. So electron configuration, what you have to basically remember are where all the blocks are. So the S block will be right here. So that's all S. P block is everywhere here. D block is all here. Then the F block, what color did I use? Is down here. Why don't I? Because I don't want to. And Mr. Jones is very capable. So at this point, you have an SPDF block of electrons. So if you need to go, let's say, to bromine, full electron configuration, you have to follow the trend. So as just like when you're reading a book, you have to finish the entire line and then go on to the next line. So read through the next line like that. So as we read this first one, we go all the way across and we finish 1s1, 1s2. So remember, helium goes right here for electron configuration. So we finished 1s2 like that. So we finished reading that page. I fought really hard to teach AP Spanish Lit, but the Profe Martinez, he was a little bit better than me. Then, as we start to read our second line, at this point we finished reading 2s2, but I had to keep reading all the way across, and then there's 2p6 because we read through 2p1, 2a, 2, 3, 4, 5, and 6. Then I read the next one, which is right here. That's 3s2. I keep reading all the way across. That's 1, 2, 3, 4, 5, 6. So that's 3p6. Then I keep going across 4s2. At this point, I'm going through my D block, but what level does my D block start with? 3. So then there's 3d10. Then finally, to get to bromine, we had to go back to the 4p and then go 1, 2, 3, 4, and then 5. Don't know what 5 is in German. Like that. So that's how you read the periodic trend. So a lot of students always ask me, hey, Mr. Lee, what does the F block start with? What does this start with? But if you just remember, the S block, the S orbital, starts on what energy level? 1. So it starts on 1, then every energy after that will have that room. So there's energy level 1s, 2s, 3s, 4s, 5s, 6s, and 7s. Then the P, so S starts on the first floor. P is going to start on what floor? Second floor. So that means P is going to start on the second floor. Then every energy level after that will have a P room. So it'll be 2P, then 3P, 4P, 5P, 6P, 7P down there. So if S starts on the first floor, P starts on the second floor, what energy level will D start with? Not 33, but 3. Why is S and P in line with each other, but not D and F? It just happens to work out that way. So 3, 4, 5, 6. That I don't really know. It just happened to do like that, or yeah, I think it just happened to it. So if S starts on the first floor, P starts on the second floor, D starts on the third floor, what energy level will F start with? 4. So it'll be 4, then 5, like that. So then if we wanted to do something more complex, let's say you wanted to get all the way to radon. Let's practice going through radon. So let me get rid of everything. So maybe. Delete, 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 delete. Just select all. No, there we go. All right, so let's get to radon. To get to radon, we have to read through the 1s. So then there's room to write. So we have the 1s2 we just finished. I'm going to need a lot more. So 1s2. Then I go to the next line. There's my 2s2. Keep reading all the way across. I finished off the 1, 2, 3, 4, 5, 6 electrons in the 2p, so it's 2p6. I finished off the 3s2, 3p6. See if you guys could beat me there. Here would be the 4s2. Then here is my 3d10. And my 4p6. 5s2. 4d10. Back to 5p6. 6s2. At this point, I guess some of you guys are typing it out. This little asterisk is letting you know, hey, it's time to go to here. So after your 6s2, that's when you have to jump down to 4f. Go through the 4f. So I'm going to just write it right here because I ran out of room. 4f14. Then once you get here, you're going back to here, which is 5d. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So finish reading that. And then finally, 6p6. So that is radon. So yeah. Kushal did the noble gas shorthand. So xenon, then 6s2, 4f14, 5d10, 6p6. Nice. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6. Ooh, you forgot a 5s2. It's 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p6. Xenon, 6s2, 4f14, 5d10, 6p6. Good. So electron configuration hopefully isn't that bad. Once you understand how to read everything, then I personally think it's not that bad. Might be bad for you, but not for me. Thank you. So that's electron configuration. Any other questions on that? Want more practice, more of this. All right, let's see. Principles, so the rules. And then subshell shapes. Really, if you do need to know the subshell shapes. Subshell shapes. Wow. Tongue twister. So, subshell shapes. S represents sphere, and it's three-dimensional. It's hard to draw three-dimensionally, but you're drawing a sphere. For P is for peanut shape, and in all three axes. You have one going in this direction, one going up and down, and one going out and back. D is double peanut. I won't have you guys draw that. And then F is flower. It gets more convoluted. It depends. I might give you the graph. You might have to draw the axes. I'll probably give you the axes if you have to draw. And pretty much if I told you to show an electron in, let's say, like S2, all you have to do is draw the sphere and then draw two dots somewhere on the sphere. But let's talk about this. If I wanted you to draw a P3, what would you have to do? Yeah, I'll give you the chart so you don't have to like memorize that hydrogen energy level chart. So then if I told you to draw like a P3 electrons, remember each electron wants their own orbital, meaning you would have to draw all three of these and then draw one electron here, and one electron there. Where a P5 is, then you would start to double up, one right here and like one right there. Yeah, so that's essentially what you just do. You just draw the shape of the orbitals, and remember the orbitals, they're not physical structures where they're a hard sphere. This is just saying anywhere, the electron could be anywhere in this sphere area. So the sphere is just showing you the probability of where the electron will be. Will we ever have to draw these in normal chem? Possibly. But not double peanut or flour. All right, so the last thing we'll talk about are the rules. Can you speak in the past tense in Spanish? Preterite or imperfecto? There's both. I could say, yo hablé en español cuando yo estudiaba en la escuela secundaria. Something like that. What are we talking about? Oh, the rules. Off-bows principle. Off-bow. This literally means in German to fill up. So now you think, all right, how do electrons fill up? This is the one where you could say electrons are lazy, so they want to fill up lower energy levels first before going to higher energy level. Do you know any French? Parlez français? Oui, oui. Porque also she speaks in past tense and I know what it means. So that's Aufbau's principle. Just they're lazy, so they want to fill up the lower energy levels first before moving on. Hund's rule, where some of you got points off. Hund's rule is there's two parts. Electrons will singly occupy each orbital before doubling up. And single electrons have same spin. That's Hund's rule. This is the one that electrons don't like each other. Then the third one is Pauli's exclusion principle. That's the one that says electrons sharing an orbital will have opposite spin. Electrons are all special and unique. Perfecto. So 105, 2, 1, basically 10. That was rules to fill orbitals. All right, any other questions? Nada. Easy test. So can we actually have it tomorrow? I'll send your Guam leader your test. Do you remember who your Guam leader is? Is it Savvy? All right, I'll end the recording.